Hello, you hear me now? Hello? You hear me now?
Yes.
Okay. Sorry, thanks for letting us know. Fortunately, you already seen this definition many times, so you haven't missed out too much. So now if we have a so-called Markov partition, then we can construct a matrix which represents the transitions of this dynamical system. So for instance, in this case, you would have two subintervals, A and B, and you will see that the dynamics works like this. The interval A is sent to the union of A and B, and the interval B is sent to the interval A. And so you can just compute this matrix, which represents the transitions. And you probably know that if you compute the lapse of the nth iterate, you take powers of this matrix. And so the growth rate of this number of laps will be represented by the leading eigenvalue of this matrix. And so the leading eigenvalue in this case is the classical golden mean. And in particular, it's a nice algebraic number, which is always going to be the case when you have a system which is given by a integer valued matrix. And then, well, this number is not quite the entropy, because in the definition we have this log. So we have to take e to the entropy. So this number, we call it the growth rate rather than the entropy. And basically, it's the same amount of information. OK, so this is a very classical, of course. What are just sort of general questions that one might ask about these eigenvalues in general whenever you have a system with a Markov partition, or for instance, a postcritically finite polynomial? Well, first of all, general question, what is the meaning of the other eigenvalues? The leading eigenvalue, of course, is the entropy. What is the meaning of the other? Well, this, of course, for things like shifts of finite type is well known. These are related to ergodicity and mixing, for instance. For instance, if you have only one eigenvalue of maximum modulus and everything else is in a smaller radius, while you have mixing and even exponential mixing, and the gap is related to the rate of mixing and so forth. So this is, of course, classical questions. Another question which is sort of related, which we will kind of address, is how intrinsic are the other eigenvalues? Because usually in nature, so to speak, you have a dynamical system and you have some coding. Like before, you have a polynomial and you have a coding with the matrix, and then you have a bunch of eigenvalues that are given from this matrix. But in principle, maybe you can change the coding and you get another matrix. And clearly, the leading eigenvalue is the entropy, so this is dynamical. And how about the other ones? Are they also somehow dynamical? Are they also intrinsic in some sense? And one thing that you could note is also there's some relation with algebra, because here's a very simple observation that if lambda is this growth rate and you take another lambda prime, which is the Galois conjugate, so it's also a root of the same minimal polynomial, well, whatever matrix you write that has lambda as eigenvalue, it also has lambda prime, just because it has integer values. So the algebra tells you that these Galois conjugates at least are somewhat intrinsic. If you know the entropy, these ones also you also carry. But so, for instance, Thurston was interested in the following question, and other people are. So what are the algebraic numbers that can arise as growth rates for critically finite polynomials, for instance? And in fact, one necessary condition is that by the Perron-Frobenius theorem, there have to be Perron numbers. So what's a Perron number? Is a number which is bigger or equal in modulus than all its Galois conjugates. This is just because this is a leading eigenvalue of a matrix, so this has to be true. And Thurston, kind of interestingly, in his last paper, proved the converse, that any Perron number, in fact, is the growth rate of some real postcritically finite polynomial. However, he did not put a bound on the degree. So here, we pick any Perron number, and there is some polynomial of some degree, which could be very high, which realizes this number. So then the next question would be, what if you fix the degree of the polynomial? So for instance, what if you just consider quadratic polynomials? Then the previous theorem is likely false. But still, you want to maybe characterize what are all these algebraic numbers that arise as entropies, growth rates of quadratic polynomials with a nice dynamical condition with this postcritical fact. Okay, maybe it's the right time to check for questions or clarifications from the audience. Yes. So Galois conjugate means that you take lambda as an algebraic number, and it has a minimal polynomial. So it has a polynomial of lowest possible degree with integer coefficient that has this as a root. And the other roots of this minimal polynomial are the Galois conjugates. So you see that these are attached in a pretty canonical way. You don't have to choose a model for that to be there. Yeah. So if you have square root of 5 plus 1 over 2, you also have square root 1 minus square root of 5 over 2. This one's come for free. Other questions, maybe? Okay, so now let's go a bit more into the classical dynamics of quadratic polynomials. So of course, people have studied entropy over the real quadratic maps for a long, long time, starting from Milner and Thurston in the 70s, and even before that. So you can consider the real quadratic family z squared plus c. And classical question in dynamics is how is the entropy changing as you change the parameter? And of course, so Milner and Thurston studied this function, and they plotted this famous picture where basically, in fact, here they plot the entropy of this quadratic family as a function of the parameter. In fact, the parameterization that they choose is not z squared plus c, but is the sort of logistic one. So a times x times 1 minus x. So this show, in fact, implies that the entropy is increasing as a function of a, while if you plot it as a function of c, this would be decreasing. But in any case, what the two important points are that this function is continuous and it's monotone. So as you increase the parameter, as you go towards the tip of the Mandelbrot set, the entropy goes up. And sometimes, however, it doesn't go strictly up. There could be some plateaus. So you see that this function, in fact, is a fairly complicated fractal structure, but still it's monotone. So these are the continuity and monotonicity are the two main properties. So there's a question from the chat. Oh, okay. Okay, so and now what Thurston wanted to do later in his life, towards the end of his life, unfortunately, is to extend this theory to complex polynomials. And I've talked a lot about this before. And so basically, in fact, some easy way to extend this would be to just consider this as a map on the Riemann sphere. But that would be somehow the easy extension, but this is not in the sense very interesting from the point of view of entropy, because then for every parameter you obtain the same number. So you take log of the degree. So there is no variation as you change the parameter. So this doesn't tell you much about the geometry of the parameters. So Thurston considered an extension of this theory. Instead of looking at the map of the interval, he looks at the map of a tree. So he looks at the map of what's called the Hubbard. So, and this is what the core entropy is about. So, okay, so everybody should be familiar with the definition of Mandelbrot set, most likely in this conference. And also we know that uniformizing the exterior of the Mandelbrot set is somewhat easy, even though the Mandelbrot set itself is a very complicated fractal set. But you can apply the Riemann uniformization map on the outside, and for each angle theta in polar coordinates, you can obtain a ray on the other side. So these are so-called external rays. So for each theta, there is this curve on the outside of the Mandelbrot set. And conjecturally, the very big conjecture is that all these rays for each theta land. And this is closely related to the local connectedness of the Mandelbrot set conjecture. But in any case, for instance, we know that for theta rational multiple of 2 pi, then we know already that this ray lands. And so you can describe points on the boundary of the Mandelbrot set by looking at this coordinate. And so this is the definition of the core entropy. So first of all, we recall what's the notion of Hubbard tree. So remember that for the real maps, you have an interval, which is invariant by the forward iteration, while for complex maps, you don't have an interval, but you have rather a tree, which is the Hubbard tree. So what is the Hubbard tree? Well, the Hubbard tree is the following. We take the critical point. So let's say we take the critical point is at 0, and you take its forward orbit. So in particular, if it's finite, you just get this finitely many points. And then there is a canonical way to connect them in a way that with a path that stays inside the filled Giulio set. And well, except for the Fatou components, this path would be unique. And inside the Fatou components, you can find a canonical way to define it. This is not so complicated, but in any case, you connect these points in the forward orbit of the critical point, and you get this tree-like structure, which is the so-called Hubbard. And what's interesting about the Hubbard tree is that the map, this polynomial, acts on the Hubbard tree, meaning that the Hubbard tree is forward invariant. Of course, it's not backward invariant, because if you take backward iterations, you're going to get the whole Giulio set. Yes? Oh, yeah. In this case, we don't care about the local connectivity problem. So yes.
Statement.
Right. So yeah, this is just a notation. So x and y are 2 points on the tree. And I denote this segment, the arc between x and y. And now in the upper definition, I take, instead of x and y, I take all the points in the postcritical orbit. So it's the union of all the segments between the postcritical orbit. So fmc0, you can replace x by fmc0 and y by fnc0, and you take the union of all these arcs. Yeah. Any other questions about the definition? Okay, and then we take the map here. So the map, of course, by definition, the forward orbit is forward invariant, and then also this sort of convex hull is also. So this is what Thurston defined as core entropy. So if we start with the Giulio set, which is connected and locally connected, we can take as the core entropy as the entropy of the restriction of this map on its Hubbard. And in fact, to begin with, we're going to just begin with postcritically finite ones. So then there's really no question whatsoever what the tree looks like. And then we're going to extend to the other. Okay, so anyways, this is the definition. So for each map, I give you this tree, and you attach the entropy of the map restricted to the tree. So you give a number. So for each map, you have. And so the question that Thurston asked here is, what happens when you change f? So okay, maybe let's first give a example. So if we start with, say, Capelli map, so map of period 4, where the orbit is of a critical point is this 4 points, then the tree is a Y-shaped tree. And so we have 4 intervals, and we can construct a Markov partition using these 4 intervals. And then we can track the dynamics of these 4 intervals. So maybe an exercise for the audience, if you're bored, what's the image of A in this map? So this point, where does this point go? Point goes here, right? So A goes to B. And what about, where does B go? C, very good. And how about C? C doesn't go to D because, well, it does, but kind of, not really. Yeah, C goes to A union B. So you see that you can reconstruct the Markov partition here. And once you have the Markov partition, you have the matrix. And then you can take the minimum, the characteristic polynomial of this matrix. And this has various roots. So you see it's degree 4, so it has 4 roots. And what we care mostly about is the main one, so the biggest root, which is the entropy. And so that's the entropy. But now we're going to also be interested in the other ones. So for instance, so what about the other ones? Is this polynomial irreducible or not? And things like this. Okay, so and then, yeah, so let's go back to the classical question about core entropy is what happens when you change the parameter. So we start with the rational angle. We associate to this rational angle a number, which is the core entropy of the polynomial with external array theta. And we plot the function as theta varies. So now theta is a rational number between 0 and 1, and you can plot this function. And this is the famous picture of Thurston. So basically what we looked at is you change the angle from 0 to 1/2, and then from 1/2 to 1, and then the y coordinate you plot the entropy. And here you already see many things. So in particular, you see that the biggest one, the biggest entropy is reached at 1/2. So it's here. And this is the tip of the Mandelbrot set. And well, at 0, the entropy is 0, but it's also 0 in many other places, in fact. And it turns out that these places are the angles that land on the main molecule. So what is the main molecule? Well, it's a chain of components attached to the main cardinal. And so you see that this function is extremely fractal. And the question that I always like to ask here is if you can you see the Mandelbrot set in this picture? Meaning that, okay, if you present it like this, you're looking at the Mandelbrot set from the outside, from the circle at infinity, and then it's kind of not completely clear how this spikes are related to the geometry and combinatorics of the Mandelbrot set, but they are. And in fact, you can maybe understand a little bit better if you plot this as a function of C. So here there's 3 different views of this entropy function. So I take z squared plus c, and c is the parameter on the xy axis, and on the z axis I plot the entropy. And so you see that this function is monotone. So if you start from the inside, so in the main cardioid, the function is 0 in this purple lake, so to speak, which is the main cardioid, and not just the main cardioid, but everything which is attached to the main cardioid. So all this main molecule. But then if you go towards tips of the Mandelbrot set, so if you go toward the 1/2 tip, but also the other tips of the Mandelbrot set, this function is increased. So you see that you have a monotonicity property, at least from this picture, that the entropy still increases as you keep going far and far from the center of the map. And also, it's kind of cute to note that if you look at the side view, the projection to the side, you see a function here. And this function is the same function as the Milnor and Thurston entropy function, which makes only sense because you're looking at the real line inside the Mandelbrot set. And so you're just plotting the good old entropy. So this for entropy restricts to the classical entropy for real. Are there any questions, comments here? Okay, so And so first of all, here we do have another notion of monotonicity. So in particular, we see that, okay, first of all, if two rays land at the same point, so if two angles have their two rays that land at the same point, well, the entropies have to be the same. That's obvious because they represent the same dynamical system. But, and in fact, there is an ordering which is given by the Mandelbrot set, which is related to its Bain structure. So basically you can realize that the Mandelbrot set has a tree-like structure. So whenever, yeah, you have, if you have 2 points on the Mandelbrot set, you can say that there's a partial order. So for instance, so you have a 0, which is the center, and you have a parameter, let's say C2, which is here. Well, we can say that the point C1 is less than C2 if it's in between. So if it's in between C2 and 0. So you can draw this arc, and we say that if C1 is on the vein from 0 to C2, well, this we define as being C1 less in this Mandelbrot order than C2. Yeah, okay. Well, I mean, I'm done anyways. Yeah, so anyways, so yeah, so sorry for the online participants, but this will be, that's it. So in any case, what is known here is that the entropy indeed respects this monotonicity. So if you have a point which is closer to the main cardioid than the other one, then the entropy here will be less or equal than the entropy of the other. So this is the monotony. And then the question, there was a famous question asked by Thurston and so forth, was whether this is actually a continuous function. And in particular, is a continuous function of this parameter theta. And the answer is yes. So that's what I proved a few years ago. And then this other proof of Tiepot-Schleicher. So in any case, this function indeed is continuous, even though it's very highly non-monotone. And I mean, and the high non-monotonicity, arises from the fact that you're looking at the function of the external rays. So you're looking from the outside of the Mandelbrot set. While if you look from the inside, so if you go along this tree structure, then there is some monotonicity. And also the regularity properties of this function are very notable. In particular, this function is continuous, but whenever the function is 0, then it's not locally Hölder continuous. And on the other hand, when the value of the function is bigger, then the Hölder exponent of this function makes sense. And in fact, basically the Hölder exponent of this function equals the value of this function at this point. So this is extremely strong property of this entropy function. And actually it happens in other cases in dynamics, for instance, for some open dynamical systems. But in any case, this is a very strong self-parameterizing. But anyway, this maybe is not the core of what I want to talk about, but rather this, we want to generalize this monotonicity and continuity. Yes? Yeah, eventually, because you first define it for irrationals, and then you extend it for irrationals. So in fact, you can define a canonical way to extend it to irrationals, and then you prove this property. Yeah.
Thank you.
Yeah. Of course, the slightly annoying thing is if the Giulio set, corresponding Giulio set, is not locally connected, well, you get this function, you have this number. And now how that relates to the actual geometry in the complex plane, well, that is a bit of a tricky issue. But in any case, there is a canonical way to extend this function from the rationals to the irrationals. Other questions or comments? So far I haven't talked in the detail about the teapot yet. So let's actually go to the teapot. So the teapot arises from considering not just the main, the leading eigenvalue, but the other eigenvalues. And in particular, so Thurston also plotted this famous picture in this last, or maybe second to last unfinished paper, which is he considered the family of real quadratic polynomials. And for each real quadratic postcritically finite polynomial, he plotted all the eigenvalues for this Markov matrix. And then he put together, stacking one on top of each other, all this enormous number of eigenvalues. So this is like an enormous number of eigenvalues stacked one on top of each other. And the coloring has to do with the density. So the sense that for every pixel, the pixel is whiter if there are more eigenvalues. So you have a countable family of eigenvalues, but then if you take the closure of that, it definitely looks like there's a lot of fractal structure going on. And so this one I call the entropy spectrum, and maybe some other people call it the Thurston set. There's so many things named after Thurston, it becomes. But in any case, so what is the formal definition? So here's the formal definition. So there's variations of this. In fact, it's not even clear what Thurston himself drew, because there's possible variations, but this is one formal way. So you take all critically periodic parameters. So you take of all postcritically finite parameters, only the ones that are purely periodic. And you plot, so you consider lambda, which is the growth rate. And then you consider for each lambda all its Galois conjugates. So you plot lambda, and which is an algebraic number, and then all its Galois conjugates. So you have finitely many algebraic numbers for each parameter. And then you take the union. So you just put all of them on top of each other. And then we just take the closure. And yeah. And so this is the picture. And okay, there's variations. You can do the density plot the other way. Then it just, so you see that, first of all, there's a big hole in the middle. So this another name for this object is the bagel. You can guess why. And you see that there is a big hole in the middle, which is not so complete, not hard to explain. And there appears to be that this eigenvalues, they concentrate very heavily on the near the unit disk. So in fact, it appears that there is a neighborhood of the unit disk that is contained in this set. Also, it's kind of interesting to know. So the real eigenvalues, of course, are on the real axis. The entropies are on the positive real axis. However, there's also some negative real numbers that arise. And also you see these holes. Okay, these holes are kind of tricky because there's two types of holes. There are holes near the roots of unity, which appear, but they only appear because of numerical approximation. So it's just the way you compute them. You cannot get very, very close to the roots of unity. But also it turns out that, Caligari, Koch, and Walker, they also showed that there are indeed real holes. So there are some real holes in there, not at the roots of unity. So this is, of course, very rich fractal set. And this is not a density plot, but just take all of them. And it's also very apparent if you've seen this picture before, coming from either number theory or mathematical physics. I mean, there's many places where this fractals appear. So if you look at the polynomials with coefficients, say plus or minus 1, so just those, and you take the union of all the roots of all of them, well, you get such fractal sets. So clearly, it's very close, at least in spirit. So you can see the comparison. We have the first one on the left, and we have this set of roots of polynomials with coefficients plus or minus 1 to the right. And it turns out that it is indeed a theorem, which I proved 2 years ago, that inside the unit disk, these two sets are the same. However, on the other hand, if you take the outside part, you see that on the right-hand side, the right-hand side picture is invariant by taking x goes to 1 over x, so or complex conjugate, or inversion, sorry. So basically, whatever you see inside, you see outside, while on the left, there are two different, very different behaviors from what happens inside and what happens outside. Questions or doubts? Yes?
So will be there a difference if you take not just critically periodic, but for instance, postcritically finite?
Yeah, unfortunately, yes. So yeah. So basically, when Thurston defined this, it was a bit unclear. But so it turns out that, so if I remember correctly, on the outside, it doesn't matter. So you get the same set, but in the inside, you actually get a different set. And this has to do with the fact that when you compute this entropy using, for instance, kneading theory, then the polynomials and power series that you get have coefficients plus or minus 1. But then if you look at the postcritically finite and not critically periodic ones, then you get also 2 sometimes as a coefficient. And so in fact, the sets are indeed different. So yeah, so there are slight variations. Yeah. Okay, so and in fact, okay, this is another very similar set when you take polynomials of coefficients 0 or 1. Yeah.
I was gonna ask if you can comment on the 6 dots that appear, the 6 black dots that appear on both.
Yeah, I did. Yeah, so yeah, it's basically what I said. So for roots of unity, so these 6 black dots are roots of unity, and also +1 and -1. So whenever, if you compute this, usually by taking low degree polynomials, you will see holes there, but then you can prove that as the degree increases, these holes get filled in. So this 6 dots eventually, if you keep doing this numerical approximation better and better, they will get filled in. However, there still exist some genuine holes which have fractal boundary. They're more complicated, but they're much harder. They're harder to see. Yeah. Okay, so let me, in the interest of time, see. So okay, you can also consider coefficients 0 and 1, and it's not quite the same, but of course, it's similar flavor, but it's different set, please. Okay, so here's the theorem that I proved at some point. Is indeed that the Thurston set is connected and locally connected. And indeed, it contains a neighborhood of the unit circle. And the other thing which is kind of remarkable is this set is closed under taking nth roots. So if I take a complex number, which is in the set, any complex root of that also belongs to the same set. And this is related to renormalization, because basically, if you take a polynomial and you take some number n, you can do the tuning of this polynomial by some polynomial of period n. And it turns out that as you do the tuning, if you study what happens to the kneading polynomial of that tuned copy, you will see that the roots will the polynomial will be replaced by the polynomial p of t to the n. So that's how this phenomenon appears. And so immediately, of course, as a corollary of 3, you see that the unit circle is in there because you take any point and you take all the nth roots of that for n large, well, it could distribute on the unit circle, on the unit disk, unit circle. So you see, maybe this is one reason why there are a lot of points near the unit disk. And also I think that there's even more, but still. Okay, so, and also, yeah, as I said, inside the unit disk, these 2 sets are the same. So sigma +1 is the one where are these polynomials for plus and minus 1 coefficients, and sigma is this Thurston set. Okay, so now let me go to the teapot, at least advertise what this object is and what we could prove. So Thurston himself drew this picture, which is the original Teapot. And so what did he do? Well, maybe you cannot read, but basically what he did is, in fact, you can take either tent maps or quadratic polynomials, but for each such postcritically finite polynomial, you can compute all the eigenvalues of this Markov matrix, and you plot the z coordinate is the entropy. So the entropy is one such eigenvalue. So you see why there is this spout. So the spout just arises from the fact that you see you have here you have lambda, the lambda parameter, and then for each point lambda, if you section this, you're going to see just some finitely many points, I don't know, something like this, and including there will be the point lambda, because lambda is an eigenvalue. So that's why you have, at least you have this one. And you see that, so if you project the set just to the xy coordinate, you go back to this Bagel picture. So what is that one can prove here? So okay, so here's one definition. For real maps, you can define it again, either for polynomials or for tent maps. So the definition is this. So you take the set of parameters for which the orbit of the, say, critical point, in this case, if we do it with tent maps, the critical point is just this turning point there. And whenever this orbit is purely periodic, then you record this parameter and you construct this matrix. This matrix M lambda is the matrix. And then you take the determinant of that matrix, and the determinant of that, the characteristic polynomial of that matrix has roots, which are these values of z. So for each lambda, you plot some finite set of z's, and then you stack them on top of each other. And so that's the, okay? So this is the same thing, but for polynomials, and you see that now on the z coordinate, I plotted, instead of the entropy, I plotted the c parameter. So here you see, once again, so if you plot the c parameter, you see once again that here you have the entropy function for the real quadratic polynomial. So the spout becomes the Milnor-Thurston function. So what are the questions that you could ask? Well, again, you can ask about connectivity and local connectivity of the set, and you can ask about other questions. So for instance, is there any sort of monotonicity? And the answer is yes. And so also, so let me show you a video that Diana Davis made to show you what happens to this eigenvalues as you increase the value of lambda. So basically, you have this one parameter family of polynomials, and you plot these eigenvalues. And so let me show you what happens. So you see there are points inside the unit disk and points outside the unit disk. And it's kind of interesting. So outside the unit disk, okay, it is kind of fast what happens. But if you look carefully, you see that the points outside the unit disk, they do move continuously, even though maybe pretty fast. So they tend to collapse towards the set. When they get to the circle, they can collapse. But if you just look at the part outside, then there is certain continuity. It's kind of more interesting what happens inside. So what happens inside is not continuity. There is these points do not move continuously. However, the property that happens is you see is what we call persistence. So what's persistence? So what's persistence? Persistence is the following. So if you take this set at the different heights, basically, if you look at what happens inside the disk as you take the set at different heights, this set grows as a set. So whatever you see at a certain height, if you take the set at the bigger height, it contains the set at the lower height. So in some sense, you can compare this to monotonicity in the sense that you have some monotonicity as a set. Of course, this is not the same thing as monotonicity of entropy, but it's another phenomenon for which, as you go from say the center of the main cardioid to the tip of the Mandelbrot set, you see that this set is increased. Any questions, comments here?
A question. So I did not understand how to see this increment on the video. Is it visible?
It should be kind of visible, yeah.
Because it seems that it oscillates.
Yeah, but just, well, let's see. I think it should be visible. I mean, if you go, yeah, if you're, yeah, at the beginning, you don't see too many points, basically. I mean, you see lots of points in the near the unit disk, but as you keep going, you see that you have more and more points, and somehow these points inside don't really change. So, for instance, you have this point, you keep seeing them, and the trace inside basically keeps growing. Eventually, you will see. Eventually, you will produce the whole inside of the Thurston set that we discussed before. Also, there's maybe a 3D rendering of this Thurston teapot. Now it's flying in space. So you can see this object. Okay, so let me finish by at least stating what are the theorems. So first of all, so there were theorems first about just the real teapot. So I mean the one for, yes. So the one for real polynomials. So on the outside, we said that we have this continuity of the roots. So the roots depend continuously on the parameter. And as a consequence, you have connectedness. So in particular, on the outside, you see that you prove that the outside of the teapot is connected. And this is what I proved at this point. And then more recently, Bray, Davis, Lindsay, and Wood proved this persistence for the real teapot. So when you look at real quadratic polynomials, so you see this is how you formulate persistence. You have a point z lambda, and you take another point bigger than lambda, and lambda prime, and the point z lambda prime is also. So you can see also from this picture that you kind of see there's more and more points as you go towards the top. Okay, so now let me show you that we have, okay, I don't want to, so you can do the same I'm done basically. So you can do the same for veins in the Mandelbrot set. And this is what our new work is about. So basically you can fix a vein in a Mandelbrot set, for instance, I don't know, 1/5 vein. So vein which sprouts from the 1/5 limb of the main cardioid. And you have also one parameter family of polynomials. And again, you can take the Markov matrix associated to that. And again, you can plot the eigen. And so basically what we get is the same type of answer. So you can define a Thurston set, and the first if you look at everything which happens outside the unit circle, well, this Thurston set that you get is also path connected and locally connected. However, it's kind of annoying that inside you don't have the same characterization as for the reals, because you don't have that it's the same as this canonical set with just plus or minus and ones. So that's more complicated. And the other thing that we get indeed is the persistence. So let me show you. So the persistent is the same. So basically for every PQ vein, we can construct this teapot-like object by taking these points Z and lambda, where lambda is the entropy and Z is one of the eigen. And then we have also the same sentence that as you keep going up, so you go towards the tip of the vein, you see more and more points inside this fractal. Okay, so I think I'm out of time. So I think I'll stop here. I'll leave you with just one more picture of the teapot. Anyways, thanks a lot. Thank you.
Questions? Lima.
Thank you. Well, I have a question about this classical Thurston-Milner graph of the real entropy. So is there anything known or conjectured about geometric properties of this graph? Well, with respect to the C parameter. For example, a very naive question, any chance that this function is absolutely continuous?
So let's see. Yeah, you can go from parameterization from the theta parameter to the C parameter. In fact, this is this work of Dobbs and Mihalash, where I think if the parameter, so what's natural is the Hölder dependence with the theta parameters. But if you have other good properties, so for instance, if it's a Kolle Ekman or something like this, then you can also bring this information to a neighborhood of the C parameter. So for some parameters, you get an analog of this. I don't think for all parameters though. So I guess this is, maybe you can ask that. I forgot what is this exact statement, but
yeah, but well, the parameterization by the theta parameter is of course natural, but it's more like a combinatorial parameterization.
I understand. Yeah. No, this is a very good question, but I think but then you run into other types of questions.
Okay, so you're suggesting that it should be Hölder continuous, but any chance for absolute continuous?
I don't know. Yeah, that's a good question.
Any other questions, comments? Maybe online? If you have comments online, just unmute yourself and ask. Okay, if not, then let's thank Giulio again for a very nice talk. The next talk will be at 10.